we have learned the equations, right? So remember the quantum Fourier transform gate has this form. And let me remind you why it has this form, because each element equals to what? Do you remember? What's the elements in a quantum Fourier transform gate? Forgot? 1 over square root capital N, and then what is inside? For the kth row, jth column, what is that? Omega to the power minus kj, yeah. For the, here we assume it is the kth row, jth column, right? So then why I have 1 here, 1, 1, 1, 1, 1?
Because omega power 0.
Is a 0th row, 0th column. Yeah, very good. Okay, so let's just look at some example, okay? 1-qubit quantum Fourier transform gate. What is that? UQFT. I just call it 1 because it's 1 qubit. So how many entry do we have? What is the size of the matrix? Or what is capital N when it's 1 qubit? Small n equal to 1, capital N equals to 2 to the power 1, which is 2, correct? That's the dimension of the space, right? So I have 1 over square root 2. So I will expect a 2 by 2 matrix, which is omega to the power negative 0 times 0, omega to the power negative 0 times 1, omega to the power negative 0, 1 times 0, and then omega power to the power 1 times 1. Is that correct? Is that okay? What is omega? E to the power 2 pi I divided by n, but what is n? 2. Correct. So because of this, this is equals to e to the power I pi. And what is e to the power I pi? Cosine pi plus I sine pi, right? What is this? Well, equal to what? 1, yeah. But however, it's meaningless to do it now because it is 1. But it's meaningless to do it now because I'm not trying to evaluate omega to the power 1, right? So I'm sorry, let's just don't do this. Just stop here. Because my goal is to evaluate omega to the power negative 1, which is this term, omega to the power negative 1, right? So, which is equals to e to the power negative I pi. So what is this? It's the cosine, still the same actually, I say the wrong. It's the same. Let me just have a new row. Which is equals to cosine pi minus I sine pi, right? Actually, the result is the same. Equals to minus 1, right? So what is the matrix? What does it look like? UQFT, 1 qubit equals to 1 over square root 2. What is the first element? Omega to the power 0. 1, thank you. How about the second one? How about this one? Also 1. This one? Also 1. As we are generally shown here, right? It must be 1 on the first column and first row, no matter what the dimension is. negative 1. That is the 1-qubit gate, 1-qubit Fourier transform, quantum Fourier transform. Have you seen this before? Yeah, it turned out that this is a Hadamard gate. Okay? And then you will guess maybe the 2-qubit gates must be 2 Hadamard gates, 2 1-qubit Hadamard gate, but it is not, okay? Otherwise, it won't be interesting. Okay, so what is, then let's look at a 2-qubit quantum Fourier transform gate. And what is small n this time? How many qubits? I'm asking a trivial question. How many qubits do we have? 2. What is capital N? The dimension? 2 to the power 2 equals to 4. So it is a 4 by 4 matrix. And we know that, right? 3 qubits, 8 by 8. So how do we find it? Well, we just use the equation. Quantum Fourier transform, 2 qubits. Turns out to be 1 over square root what? Based on the equation here. 4. And what's the entry? I will give you directly. I'm sure this is 1, 1, 1, 1. Because they're all omega to the power 0. 1, 1, 1. Omega to the power 0. Okay? And this is the entry, negative I, negative 1, I, negative 1, 1, negative 1, I, negative 1, negative I. Now, of course, you don't need to memorize it. You even don't need to put it in cheat sheet, right? I would not expect you need to remember this. But we should try to understand what happened. If you look at this equation, you find that first row, of course, is 1, 1, 1, 1 because it's 0, right? First column is 1, 1, 1, 1. But let's look at the first column, right? When you go from top to bottom, what is the difference between the index? Right? Think about that. So this is 0 times 1. This is 1 times 1. This is 2 times 1. This is 3 times 1. Do you understand what I'm talking about? This is omega to the power kj, right? This is k equal to 0, j equal to 1. And then this is k equal to 1, j equal to 1. K equal to 2, j equal to 1. K equal to 3, j equal to 1, right? So when you go down, you actually increase this by omega each time. Okay, so let's look at what is omega in this case. Omega in this case is e to the power what? Can someone tell me? 2 pi I over 4 instead of over 2, right? And what is this? This is e to the power I pi over 2. So it is cosine pi over 2 plus I sine pi over 2. And what is this? I, right? This is equal to I, right? Because cosine pi over 2 is 0. And then, what is omega to the power negative 1 then? Well, 1 over I, which is equal to negative I. Right? So the reason I say this is, okay, from here to here, here to here, this is negative. So actually, we multiply this by negative omega. Then further multiply by negative omega. Further multiply that by negative omega, right? So that's why I will have, let's say, this first column. You have I, 1, negative I, negative 1I. You will actually multiply negative I, and then multiply negative I, multiply negative I. That is what you get, right? You keep going down, you keep multiplying negative I. Right? So if I know this element, I know that this must be times negative I times negative I times at negative I. I will get it, right? 1 times negative I equal to negative I. Negative I times negative I equal to negative 1 because negative times negative is 1 I times y. 1 I times I is negative 1, right? And then times negative I again, then it becomes I. Is this okay? Do you see the pattern? So this is a geometrical series with a ratio of I, right? But how about for this column? What is the ratio? Then you just think about this. This is 0 times 1, 0 times 0. And then, no, sorry, say the wrong way. 0 times 2, because this is the column 2, right? 0 times 2. And then what is this? This is what? What's K? 1 times 2, 3 times 2, 4 times 2. So the ratio is omega to the power 2. Okay? I don't know. Let me. So for example, the second column, we start with 1, and then you multiply by omega to the power negative 2, which is equals to negative 1. Because it is actually just I squared. Right? Then you will get negative 1. Then again, you multiply by negative 1, you get 1. Then again, you multiply by negative 1, you get negative 1. And that is a way for you to check if you're doing the right thing. Okay, and similarly, you can go back. This is actually omega to the power negative 3. But anyway, you see the ratio is I, right? Because 1 times I equal to I. So I continue to multiply I times I equal to negative 1. Multiply I, negative 1 times I equal to negative I. Okay, and similarly, you can see that for the row when you go from left to right, because they have the same K, but they have different J. Right? So here multiply by I, negative I, here multiply by negative 1, and here you multiply by I. Any questions? So I spend the time for this is nothing, just want you to have an idea, have a feeling, right? Although you know the equation, I hope that now you know that what a quantum Fourier transform matrix look like and what is their relationship. Every row, every column is a geometrical series, and they have a different ratio. Yeah, okay. Okay, so you can do the same thing for 3-qubit, 4-qubit. I go back to write it if you're interested. Okay, we will learn how to implement a quantum Fourier transform gate. But before that, I just want to remind you what is a swap gate and how do we, what is a multi-qubit swap gate, right? So a 2-qubit swap gate is this, if you forgot. It's like, I just call it US, right? You apply to 2-qubit AB, what is the result? BA, thank you. It's very trivial, so sometimes you feel strange, right? So easy, right? Just swap them. That's the definition we learned before. Okay, here I just want to say, how about n-qubit, right? So I assume n is if n is even, and it's the same for odd, but it's just easier for me to write the index. I assume I have n-qubit and it is even, right? Same for odd n, right? So I will write it as swap. Let's say call it n. So it means n-qubit. So I apply this to n-qubits. So I have n-qubit. I call it x0, x1, all the way to xn divided by 2 minus 1, xn divided by 2, and then continue to xn n minus 1, right? Look at this. Do I have n qubit here? Do I have n qubit? Because it goes from 0 to n minus 1, right? And n is even, so n divided by 2 is an integer. N divided by 2 minus 1 is also an integer. Right? For example, if n is n is 6, then this is 3, this is 2, and this is 5. So this is the swap gate. And by definition, right, this equals to, how do we swap it? Xn minus 1, right? Xn minus 2, and go to Xn divided by 2, Xn divided by 2 minus 1, X1, X0. So very clear. What we mean by swap is just move the last one to the first one, right? Second last to the second. Swap them. Is that okay? Just like rotating it, right? That's it. That is the implementation. Okay? And give an example. For example, if n equal to 4, then what we're talking about is U as 4 applied to x0, x1, x2, x3 equals to x3, x2, x1, x0 with n equal to 4, n divided by 2 equal to 2, n divided by 2 minus 1 equal to 1, right? Just as some numerical examples. Right? Any questions? Make sense? Why do we what? Why do I pick n over 2? It's just because I have n over 2 here. It represents the between n over 2 and n over 2 minus 1, it partitioned it into 2 parts. Yeah, so 2 and 3 are the upper one, 0 and 1 are the lower one. Yeah. I just accidentally labeled this. So you understand the meaning of n. Other questions? Oh, so very straightforward, actually. Just swap them. But just that the math will be good to understand better, right? If you can write down the index. Okay, so then I continue. I just want to show that, hey, this one, I'm doing this n-qubit swap gate. It is the same as I swapping. So this becomes a little bit, I change the notation. I'm swapping only n divided by 2 minus 1 and n divided by 2. Okay, maybe I should keep going. Swapping, which one? 1 and swapping 1 and n minus 1, and then times swapping 0 and, sorry, this is true. This is wrong. Should be n minus 2. And then swapping 0 and n minus 1. When I apply to this state. So I'm trying to break it into many 2-qubit swapping gates. So a little bit confusing. First, this is still the n-qubit state, right? And what I'm saying is that, okay, first you swap 0 and n minus 1. Then you swap 1 and n minus 2. Then you keep going. At the end, you swap n divided by 2 minus 1 and n divided by 2. Is that clear, this intention? So here I have, this is an n-qubit swap gate. What it does is, okay, swap everything together at the same time, right? Here, say I break it down into actually n divided by 2 swap gates. N divided by 2 qubit swap gates. First, swap the most significant bit and the least significant bit. And then swap the second most and second least significant bit. Keep going, right? So if you look at this, let's just do it one by one. I first apply the first gate, so these gates are still there because they're on the left, so they're unchanged. And then U as 1 n minus 2, but now I apply the first gate, swapping 0 and n minus 1 already. So this becomes xn minus 1, but x1, x2, etc. are not changed yet. Right, and same for xn minus 3. Xn minus 2 are not changed yet, but here I swap x0 to here. Do you see that? This one apply to this. Right, this one apply to this 2, so I become n minus 1 and 0. Make sense? Is it confusing? Confusing?
So the quantum circuit is like almost like a double staircase.
Yeah. I'm going to show that. Yeah, good thinking. Yeah. So, but do you understand what I'm talking about? n-qubit gate, I break it down into n divided by 2-qubit gate. Okay, so let me run one more gate, then maybe it will be clearer, right? So then this one, S n divided by 2 minus 1 n divided by 2 ... Now I don't have this already because I swap also xn minus 2, but then the rest are the same. And this one has x2, x1, x0, right? So this time I finish the swapping of these two. Because I swap 1 and n minus 2. So now n minus 2 is here and 1 is here. Okay? Any questions? Yeah. This is the tensor product of the two of swap gates. Yeah. No, I said not tensor product. This is the continuous application of the gate. It's not a tensor product. Now you apply a NOT gate, LAN gate like this one. But here I actually skip something very important. When I only say swapping 1 and minus 2, right, means I only affect this qubit and this qubit. I actually also need to write down the identity gate for other qubit, and that is the tensor product of those identity gates with this gate, right? Because this is n qubits, every quantum gates need to be n qubits, right? But here it's only 2 qubit. Because I'm lazy, I assume that I already put the tensor product with identity gate to make it a 2-qubit gate, right? But from this gate to this gate is just a completely new gate. They are not tensor product of each other. Just a sequential application of quantum gate. So that's a good question.
So, are two tensor products of two swap gates and apply on a vector, does that swap 0 and 1 together, so it becomes 1, 0, and then 2, 3, so that becomes 3, 2, or does it go all the way in?
You say apply tensor product of what?
Two swap gates together?
This one and this?
No, that,
Swap gate, here we're only swapping 2 qubit, right? In this case. So are you saying two qubit swap gate?
two qubit, yeah.
So you mean, for example, you want to do them at the same time?
Yeah.
Yeah, then you need to do the tensor product. You can say they are the same. It is the same as here. So there's just a different way. Okay, let me draw the circuit, then you will see why they are the same. Okay, so let me just draw what we have just done, right? So for example, I have n equals to 5. So let's say the input is 1, 0, 1, 0, 0. then what is the symbol for the swap gate? It will be something like this, like what he just said, right? And to make it symmetric, I will draw it in this way. So this is the symbol of a 5-qubit swap gate. It's different from IBM Q, but anyway, what is the output? Well, I apply 5-qubit swap gate to this one. By definition, 0, 0, 1, 0, 1. Right, it's 5-qubit. But we just say that I can do it pairwise. I will first swap the first qubit and the second qubit with a 2-qubit gate. So here may be a little bit interesting. This part, right, this gate is actually a 5-qubit gate. Right? But for this one is just a 2-qubit gate. Do you see that? This one, what I'm trying to say, I swap the most significant bit and the least significant bit. Then I don't do anything for my other qubit, they will just come here. This is confusing. And then I apply another swap gate. Right? Maybe I should draw this using another 9, not to get you confused. Right, so that clearly show that this is a 2-qubit gate. Do you see what I'm trying to do? First, we swap this 2-qubit, and then we apply another gate to swap these 2-qubits. And then for the last one, because it's odd, we don't need to swap it. It just swap with itself. So it go through. Right? So again, if we look at this circuit, the input was 1, 0, 1, 0, 0. When you reach this part, it becomes what after the first swap gate? 0, 0, 1, 0, 1. Because I swap this qubit and this qubit, so I get 0 and 1. The middle three are not changed. Is that okay? And then eventually, what do I get when I reach here? Well, I'm going to swap this and this, right? But both are 0, so they are also looks like no change. Is that okay? But in IBMQ, right, what does it look like for the symbol? It will be something like this. First, we swap these two, and then we swap these two. But this one is just an identity gate, right? This is the same. Okay, and this is a 5-qubit swap gate. And then I'll go back to your question. You say, hey, can I actually just like saying that this is a tensor product of the swap of this 2-qubit and the swap of this 2-qubit? You can say that, right? Because if you make it really, really close to each other, you can build a gate, but that becomes a 4-qubit gate. But if you apply it sequentially, then just put it this back. This is time, right? So they are the same. Yeah. But if you do it together, become a 4 qubit gates. That's not our purpose, right? So yeah. Yeah. So yeah, it's almost impossible to build a 100 qubit gate because of the physics, right? You need to involve all of 100 qubit to interact together. And now I do want 52 qubit gates. That is much easier. Yeah. Okay, so I introduced this. Just hope you understand the meaning of swap gate. Then let's go to quantum Fourier transform, right? So now, let's say what is how do you implement 1 qubit gate? What is the circuit of 1 qubit gate? Thank you. Hadamard, we just proved that 1 qubit is Hadamard gate, right? So if I ask you to implement 1 qubit quantum Fourier transform, just put a Hadamard gate. Done. Okay, this is easy. So how about 2 qubit gates? We are not going to derive it. It can be derived. Very troublesome. When the first time I taught this, I tried to derive, and actually I just confused everyone. And it's meaningless to spend time for this class. So 2 qubit gates, it is what? It is something like this. I just draw the circuit for you. Of course, you have a MSB. So here I put LSB. Just like IBMQ, I put LSB on top, MSB at bottom because it's 2 qubit. The MSB get a Hadamard gate, and then we have a gate called control phase shift for negative 2 pi divided by 2 to the power 2. Okay, I will explain more. And then Hadamard gate. And then eventually you have this swap gate. And that is the output. Here you get QFT. Maybe I should say that, for example, your input is psi, then the output becomes UQFT to operate for on psi. Is this okay? First, what we're doing, you understand? I'm trying to draw a circuit to implement the 2 qubit QFT, which is this one. I want to implement this matrix. And I tell you that this is how you implement. Okay? First, both of them will get Hadamard gate. But and at the end, they will get swap gate. But more importantly is this gate. What type of gate is this? First of all, what is this PS minus 2 pi divided by 2 pi squared? So this means that we apply a phase shift gate, right? PS, if you remember, the PS gate with this angle, 2 pi divided by, should be negative 2 pi divided by 2 to the power 2, right? 2 squared. It is equal to this. 1, 0, 0, e to the power negative 2 pi I divided by 2 to the power 2. Okay, this is, if you forgot, you go back to check what we learned for phase shift gate. Phase shift gate is e to the power I phi. And here the phi is, right, just remember, phase shift gates of phi equals to 1, 0, 0, e to the power I phi. That is the phase shift gates we define in this class. And now phi equals to 2 pi divided by 2 to the power 2. Is that okay? This is phase shift gate. What is e to the power negative 2 pi I to the power 2 square? Is equal to negative pi I divided by 2, right? 2 divided by 4. You may say, why you want to put 2 to the power 2 instead of 4 at the beginning, right? There's a reason I will show you later. Okay? And what is this? This is cosine negative pi over 2 or and minus I sine pi over 2, right? Which is equal to negative I. Am I right? Equals to negative I. Right? So that it means the phase shift gate is 1, 0, 0, I, negative I. Now this is phase shift gate, but what we are implementing here is not a phase shift. What is this gate? Control phase shift. Very good. Which one is the control qubit? LSB is the control qubit, right? This is control. And this is the target. Yeah, so it's the same. Okay, I was a little bit worried. So what is this control phase shift gate look like? If you remember control, what's the meaning of control? If the least significant bit is 0, you do nothing, right? If the least significant bit is 1, then you apply the control phase shift gate. But for control phase shift gate, you only get the phase shift when the target qubit is 1. Right? So only for 1, 1 situation, you will get the phase shift. So let me give you the result, and then we can discuss a little bit more is how come we have this. So it's going to be like this. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, negative I. This negative I, of course, is e to the power negative 2 pi I divided by 2 to the power 2. Right? And because we have 0, 0, 0, 1, 1, 0, and 1, oh. Okay, I hope the recording is okay. Still running. So this is a very important concept. Are you okay with this? Anyone has question? Why I only have the phase applied to the last corner? Again, you don't apply the phase shift gate if the control qubit is 0, right? If it is 0, you don't apply. The control qubit 0 is for this row and this row. You don't apply, then of course it is identity. And when you apply, if the control qubit is 1, which is this row and this row. But if the target qubit is 0, again you only apply 1, right? But if the target qubit is 1, then you apply the phase, which is negative 1. That's why you get this control phase shift. And let's say you really forgot how you construct this matrix. Just remember the elements of the matrix is I, CPS, I, J, right? For the I row, J column, right? So you try to apply them. For example, the last one is 1, 1, control phase shift 1, 1. Right, this one you need to go back, right? As I told you before, the elements is just the I row J column is just the the bra of the ith basis vector times the gate times the jth basis vector, right? So for this element is the 1 1 basis vector sandwich the CPS, right? And then what is this CPS applied to 1 1 based on our definition? Control qubit is 1, so apply the phase shift, but then your target is 1, so you do get the phase shift of e to the power I pi. And that's why you take it out, and this is orthogonal, so that's why you get -1. Okay, think about that. Any questions? Why we don't apply the phase shift when it is 0? Because that is the definition. You see that? This is the matrix 1 0 0 E I phi. So if it is 0, not the control version, not control phase shift, just phase shift itself. It is 0. This is the vector is 1 0, right? You multiply it, you don't get the phase. Yeah. Phase shift gate by definition only apply to 1. Okay, good. What do you need to learn? You don't need to memorize this circuit, right? It's good to put in cheat sheet just as a practice. But more importantly, this one challenges us again the meaning of control gate. I hope you understand what happened here. Instead of just control not, now have control phase shift. In the past, we talked about control Z gate. And later, we have more control gates in other algorithms. They are very important. Okay? So with this, then let's practice the math, right? So we just say that the quantum Fourier transform of a 2-qubit gate is the swap gate times I tensor product H times control phase shift times H tensor product I. Did we say that? Maybe we did not do that explicitly, but let's take a look. The circuit go from right to left to right, right? So you do multiplication, you start from this one, right? So you should have the right part at the left part, right? So first you have what? H tensor product I. Do you agree? This is H tensor product I because H applied to MSB. H tensor product I. Then we apply a control phase shift gate. Control phase shift. Then we apply Hadamard gate to this significant bit, so it's I tensor product H. I tensor product H. Then we apply the swap gate. Swap gate. Is that okay? Yeah.
For the control phase shift, the normal is from the MFB.
So yeah, for control phase shift gates, you can have the control from the MSB and then the target at the LSB, right? Yeah. But you will find that they have the same matrix form because it only happened at 1 1. So now you actually cannot distinguish which one is the control gate. Now this is something very special. And then because of this, you will be able to do a phase shift to MSB, but actually you transfer to LSB for some special purpose. Yeah, so because they share the phase together in some sense. Yeah, because once I get this phase, you cannot say whether this phase is for the control qubit or for the target qubit. Then you can use it for the purpose you want to do later. Yeah, so that's a good question. Okay, so let's just practice math. What is a swap gate? It's easy. 1 0 0 0 0 1 0 0 1 0 0 1 0 0 0 0 0 1, right? It's identity, but only change the second and third row. What is the identity gates tensor product Hadamard gate? Well, I just copy Hadamard gate to every identity block, right? So it's 1 1 1 negative 1, and this is 0. 1 1 1 negative 1. If you remember, again, this was 1 1 0 0 for the identity, and then I put H2 here. 1 1 negative 1 1 1 negative 1 1 1 1 negative 1, right? And 0 give you 0. What is a control phase shift gate? We just derived it. It's 1 0 0 0 0 1 0 0 0 0 1 0 0 0 0 negative I. Right? Negative I. That's the control phase shift gate. And then finally, do not forget the 1 over square root 2. I have Hadamard gate tensor product I. Hadamard gate was 1, 1, 1, negative 1. Each of them multiply identity gate. So it's 1, 0, 0, 1 identity gate. 1, 0, 0, 1. 1, 0, 0, 1. But negative 1, 0, 0, negative 1 because this block is negative 1 for the Hadamard gate. Okay? Then the rest is just multiplication. I take this 1 over square root, 2 of them becomes 1/2. Then I multiply the first one. Again, I hope that you can do it easily because this is row times column and I only have 1 here. Basically what I do is just copy this row, right? So the first one is 1, 1, 0, 0. The second one only have 1, 1. So I just copy the third row to the second row, right? So it becomes 0, 0, 0, 1, 1. Then the third one, just copy the second row to the third row, 1, negative 1, 0, 0. The last one is just as it is, right? So let me repeat again. For example, the last one, this one times this one become this. This one times this become this, right? And because I only have 1 at the end, so this is not a filter. I only get this one 0, 0, negative. This should be 1, negative 1, right? That's what I get. And now I do the multiplication of these two, and you can see that this is almost just an identity matrix, right? So I just copy all of them, except for the last row, I need to multiply negative I instead of 1. So this is very trivial. I will just copy the first row, 1, 0, 1, 0, 0, 1, 0, 1, 1, 0, negative 1, 0. The last one will be 0, negative I, 0, I. Okay, and then I will do further multiplication. And if you look at this, this is what? This row times this column. And it will get the number from the first two rows, but they don't always together. They always only have 1, right? So this is 1 times 1, 1 times 0. So this is 1. 1 times 1, 1 times 1 times 0, 1 times 1, so 1. So basically, the first one is just to merge the first two rows. So I get 1, 1, 1, 1. For this one, what it does is just to merge this two rows, but put in the second row. So it is 1, negative I, negative 1, I, right? What I'm doing is that 1, negative I, negative I, right? Negative 1, I. Then I have this. For this one, it try to, again, merge the first two rows, but whenever it is the second one, you multiply by negative 1. So you get 1, negative 1, 1, negative 1, right? And finally, for this one, also merge the last two rows, but for this number from this row, you just do negative, right? So this one, I get 1, and then I, negative 1, negative I, right? So what I'm doing is, because 1 times 1 give me 1, and then negative, this 1 times 0 plus negative I, negative 1 times negative I give me I, right? So 1 times negative 1, and then negative 1 times I give me this. And this is what we had earlier here, okay? I will check my cheat sheet. It is 1, 1, 1, 1 negative I, negative 1 I, 1 negative 1, 1 negative 1, 1 I, negative 1, negative I. And this is the same circuit. Okay, so I show you that, I mean, hope you can go back to practice, right? This circuit does implement a 2-qubit quantum Fourier transform gate. Okay, let me pause a little bit. Any questions? You want me to explain this again? Yeah. Oh, that's because I start from here, right? I see LSB get nothing, so it's I. MSB is H, and that's why it's H tensor product I, right? And later, MSB get nothing, but LSB is H, so I have I tensor product H. Because this is MSB, this is LSB. Good question, yeah. And again, the rest is just math. That you need to know that I'm going to have a question like what we had midterm again. I want you to derive a circuit using matrix. Okay, so make sure you don't mess up. Good, so that's 2-qubit gate. How about for an n-qubit gate, right? Now it's very complicated, but for what we have learned, you will find that it's easy. First of all, again, we have MSB at the bottom, LSB at the top. At the end, swap gate. This is n-qubit swap gate. Of course, you can implement by many 2-qubit swap gate. This is what we said earlier. All you do is just swap them. Okay, that's first thing. And then I start from the left. On the left, again, you see everyone will get a Hadamard gate. Every circuit will get a Hadamard, every qubit get a Hadamard gate, right? This is just like what we see here for LSB and MSB. So that is easy. And then the rest is this. For every qubit, right, starting from the second least significant qubit, you will get a phase shift gate. After Hadamard gate, you get a control phase shift gate and controlled by the qubit smaller than you, less significant qubit than you. So for example, this is a control phase shift gate applied to the second qubit. This is the least significant. This is second least significant, right? If you cut here, this just 2-qubit quantum Fourier transform. Do you see that? This is just a 2-qubit quantum Fourier transform, what we just did. Is this okay? Okay, and what is the angle you want to shift? It's negative 2 pi divided by 2 to the power 2, where 2 is the distance to the target, to the control, the distance to control qubit plus 1. So the distance from here to the control qubit is 1, right? Because this is least significant, this is the second, right? So I plus 1, that is 2. So you do a phase shift of negative 2 pi divided by 2 to the power 2. Okay? Now how about the third qubit? You do the same thing, but you will get control gates from each of the qubit that is less significant to you. You will get the control from the one just next to you, which has a distance of 1, and the phase shift is 2 to the power 2. You also get a control phase shift to the one that is further away from you. The distance is 2, so it's 2 plus 1. You get negative 2 pi divided by 2 to the power 3. Okay, so let's pause here a little bit. You go from least significant bit. If the least significant, you just get a Hadamard gate. If not, after Hadamard gate, you get a control phase shift from those qubits that is less significant to you, right? But since you're the second least significant, you only have one that is less significant to you, or in this figure, on top of you. You only have one qubit on top of you. So this, you get controlled by that qubit. And that's it. And how much is the phase shift? Is negative 2 pi divided by 2 to the power 2, where 2 is actually the distance to the control qubit plus 1. The distance is 1, so is 1 plus 1 is 2. So now you go to the third qubit. You need to get control phase shift from every qubit on top of you. Okay, so we start with this one. I get a control, and then I get a control from this one also. But the phase shift is 2 to the power 2, because this is 1 plus 1. This is 3 because this is 2 plus 1. The distance is 2. Make sense? Now, if you go to the most significant, the bottom qubit, of course, is get control phase shifts from everyone above you, right? So from this one first, the distance is 1, so 2 to the power 2. Then the next one to it. But for the one that is furthest away from you, of course, it is n, right? I mean, n minus 1, right? Because we have n qubit. But then again, it's n minus 1 plus 1, so it's 2 to the power n. Is this clear or no? Clear? So in principle, right, you should be able to draw this circuit if you understand what I just said, right? It's not difficult to memorize if you think it this way. Of course, there's something more profound and deeper when people come up with this derivation, right? It's not from random. So let me just say one more time. This is like phi equals to 2 pi negative 2 pi divided by 2 to the power distance plus 1. Right? Distance between the control qubit and the target qubit. Okay? Yeah, so we basically done quantum Fourier transform. Here is the IBM-Q circuit. It's not difficult to understand now, I hope, because here is how many qubits, first of all, 3 qubits, right? So swap gate. That is correct. This is a 2 qubit swap gate is 3, so this one doesn't need to get swapped. So you recognize this. Before that, I have H gate, H gate, H gate for each of the qubit. For the second least significant bit, you get a control from top. This is a control phase shift. How much do you need for the phase shift? You need phi equals to negative 2 pi divided by 2 to the power 2, which is equal to negative 2 pi, negative pi divided by 2. And that is exactly this. Control phase shift negative pi divided by 2. I don't know if you can see the text. Negative pi divided by 2. Okay? And here what? I have the third qubit, control negative pi divided by 2. And this one, what is it supposed to be? Phi equal negative 2 pi divided by 2 to the power 3, because the distance from here to here is 2. The plus 1 is 3. And this is equals to negative pi divided by 4. And that's why this is negative pi divided by 4. And this is a 3-qubit quantum Fourier transform. And then I try to measure it. I start with what is the input. Do you remember what should be the input here? Or 0, 0, 0, 0, 0, right? If you write in the vector form, it's 1, 0, 0, 0, 0, 0, 0, 0, because it's 3 qubit. This one refer to 0, 0, 0, right? And this refer to 0, 0, 1, etc., all the way to 1, 1, 1. Correct? After this, what do you get? Quantum Fourier transform, what it does is that, as we shown in the previous example, it just creates an equal superposition of all states. Right? So that proves that, yeah, it is doing something related to quantum Fourier transform. And why they are not the same? Again, isn't that they should be equal superposition? Noise, thank you, because this is a real quantum computer. And why is actually pretty noisy compared to what we saw before for other circuits? Because you actually have quite a lot of gates here, swap gates, phase shift gate, control phase shift gate, Hadamard gate, control gate. You have 1, 2, 3, you have 4 2-qubit gates. The fidelity reduced a lot. That's why it's pretty ugly, right? Okay, just want to say about the quantum Fourier transform again. I just want, last time I already say it, for our quantum Fourier transform, QFT, we define it as 1 over square root n, and then the matrix is omega to the power negative kj, right? For kth row, jth column, right? But in other textbook, they call this inverse quantum Fourier transform. I mean, I just call this other, right? I just want you to know that. I just want to remind you. For our inverse quantum Fourier transform, this is equals to 1 over square root n, omega to the power kj instead of negative for the kth row and jth column. Correct? And in other textbook, they call this quantum Fourier transform. I call this others. Okay? And the reason is because we are trying to have different description about quantum Fourier transform. One of this is try to base on the discrete Fourier transform definition. One is based on how you transform the basis state. It's just like when you rotate the vector v to v nu, you can describe it as rotating the v or describe it as rotating the vector from 1, 0 to 1 dash 0 dash. But that is okay. It's just purely related to how you define it. You just need to be careful, right? So, for example, you keep thinking negative is quantum Fourier transform, but maybe a paper say that I'm doing inverse quantum Fourier transform. You find that why is negative? It's just different definition. You just switch gear, okay? Just be consistent. That will be okay. Okay, any questions? Now, if no, we will go to another topic, quantum phase estimation. This is not difficult if we understand what it is about. Now, let's just go to this. Now, for example, for a unitary matrix, okay, unitary matrix is very important because all our quantum gate are unitary matrix. So very often we want to understand the property of the unitary matrix and use it to help us do some quantum computation. And for any unitary matrix, of course, it has eigenvalues, right? Any matrix has normal matrix has eigenvalues. But its eigenvalue is not just is special. It has a unity eigenvalues. It has unity eigenvalues. What does it mean? It means its eigenvalues are in the form of e to the power I theta, or we can rewrite it as e to the power I 2 pi phi. Doesn't matter. What we're trying to say that its eigenvalue has this form, e to the power I theta. And then why we call this unity? Then of course, e to the power I theta magnitude equal to e to the power I 2 pi phi magnitude, right? Equals to 1, right? The length of e to the power I something is 1. It's on a unit circle. So they always have this vector. It's not going to get 2i, 3i, 4i, because it's a unitary matrix. That's the first thing. So I can show you, now we are going to prove it. Let me prove that it has unity eigenvalues. So assume lambda is its eigenvalue, right? Maybe I just call it, I just call this equal to lambda. The whole thing equals to lambda, right? So lambda magnitude equal to this. So unitary U apply for the eigenvector equal to lambda times the eigenvector. This is okay? The definition of eigenvalue. Eigenvalue is you apply to its eigenvector, equals to the eigenvalue times the eigenvector, right? Okay. Now, then I try to find its conjugate, the dual correspondence. What do I get? Of course, then I will get the bra of the vector, bra form, and then U dagger equals to lambda star this, right? Is this correct? That is how we find the correspondence, right? U times the cat is equal to the bra times U dagger. Right? And this one must be equal to the bra times the compressed coefficient of lambda. Right? Or on the other hand, I can just apply a dagger to it, to the left, and then I will get this. Apply dagger to this, I will get this. Okay, so I have two equations. Then, consider lambda U dagger U lambda. What I'm trying to do is just do the inner product between this one and this one. This one and this one. Isn't that this one equals to lambda star lambda, the whole thing, times lambda vector, right? If this is not clear, let me label them. If this is A, B, C, D, what I'm doing is C times A equals to D times B, right? C times A give me this, and then D times B give me this, right? B is this, D is this, and B is this. Correct? Any questions? Now, what is this? Just be very careful. This is just parentheses. I can ignore them. And this is numbers, right? And this is bra, this is cat. So what is this? Yeah. Bra inner product cat is equal to 1 because they are normalized. But so this is lambda star, lambda inner product lambda. So this is equal lambda star lambda. Make sense? Then I will also continue to do this one. This one equals to what? It's unitary. So U dagger U equals to what? Huh? U dagger U equals to I, thank you. Lambda I lambda. And what is this? 1, thank you, because lambda inner product lambda is 1, right? So I have equation 1, equation 2. So from equation 1 and equation 2, what do we get? Lambda squared equal to 1, right? Because lambda compressed number times lambda. Remember, this is just equal to lambda squared. So it means that its length equal to 1, right? So then, yeah, so it's unity, right? Lambda is unity. So lambda must be equal to e to the power I theta. I can also represent theta as 2 pi phi, right? I just said this, I say, so this is proof. Okay, so the whole thing that I have said is that, what does it do? Okay, I don't have enough space. Forgot that I need to say this. So this first, I proved that the eigenvalue of any unitary metric has unity, right? Has a unity length, has a unit length, and it is represented as e to the power I theta. So this quantum phase estimation, QPE, is to phi, okay? It's not to phi theta. Can you see it? Not see, right, for the color. But again, the eigenvalues is e to the power I theta, but we are not finding theta in that circuit. We use the circuit to find phi. Phi times 2 pi is theta. Okay? So that is the purpose of quantum phase estimation. We are not going to derive the circuit because we don't have enough time. But we will use this circuit later. But anyway, this is a quantum phase estimation circuit for Z gate. So here, Z is the unitary matrix of which the eigenvalue space is to be found. Okay, I don't know if you can read my writing. Okay, so here is a circuit for us to find the eigenvalue of Z gate. The phase of the eigenvalue of Z gate, right? So then you will see that it's pretty complicated, but here we use something called quantum Fourier transform. So quantum Fourier transform is used in this circuit to help the phase, to find the phase of the gate that we want to find. Of course, this is something very simple, right? So what do I, okay, let me see. Here yet. So let me show you an example. So what is the eigenvalue of Z gate? So Z equal to 1, 0, 0, negative 1, right? So what is eigenvalue based on definition? 1 and negative 1, because it's diagonal, 1 and negative 1, right? But this is not what we're trying to find. 1 equal to e to the power I 2 pi times 0. Negative 1 equal to e to the power I 2 pi times 1/2. Because e to the power 2 pi times 1/2 of e to the power I pi is negative 1. So I write its eigenvalue in this form. So psi equals to 0 for psi 0, for eigenvector 0, and then psi 1 equals to 1/2 for eigenvector 1. Do you see that? For the eigenvector 1, psi is 1/2. So this quantum phase estimation circuit will eventually come up with a result equal to 2 to the power 2 times psi 1. In this case, it will be 4 divided by 2, which is 1, 0. Okay, so we won't go into details. I just want you to know that the quantum phase estimation circuit uses quantum Fourier transform. Second, quantum phase estimation is used to find the phase of the eigenvalue of a unitary matrix. And that phase is represented as e to the power I2 phi, right? And to use it, for example, we have this B register, we put in the eigenvector that the corresponding eigenvector of the eigenvalue we want to find. Let's say this is E1. And then you have this control Z gate, but many times. And then go through the quantum Fourier transform. Then I will be able to find the eigenvalue of this circuit, of this corresponds to this eigenvector. Now, do you need to study this? Okay, if you don't study. However, the point is, this thing has nothing to do with quantum phase estimation. All the skill you learn here is just a general linear algebra, right? So I can just ask you to prove this without referring to any material here, right? So you don't need to memorize the circuit, really understand what's going on if you don't have time. Otherwise, take a look on my book. I have a chapter on quantum phase estimation. I'm not going to cover it, and I hope you can do that, right? And this is the implementation of the quantum phase estimation circuit. Because of time, I will just stop here. Maybe I will try again because there's something we can learn and practice. We'll do it again next time. And that's all I want to talk about quantum phase estimation. Okay, let's stop here. Let me know if you have any questions.